Okay, I'm Andrew Gorska, and this is,
I'm Sydney Lee.
and we're doing applications of partial differential equations. The three main types of PDEs you would kind of encounter in introductory PDE classes: the heat equation, which is used to model like physical quantities that diffuse across the system, such as like heat, and hence the name. And then there's the wave equation, which is a hyperbolic equation that models propagating signals, such as if you plucked a musical instrument string or you dropped a stone in water, you would see the wave equation can model how the disruption propagates. And then there's the Ploss equation, which is known as the elliptic equation, and this is used to model fluid dynamics. So you could design like an airplane wing or like a speedboat or something. And for our presentation, we're focusing on the heat equation because it's the most like intuitive. When you see the solution and see it graphed, you'll enjoy it, and we did. So we're going to be doing two types of heat equation problems. These are both one-dimensional problems, and the thing about PDE problems is, unlike ODEs, when you're working with a problem, you're just working from the information of an initial condition and seeing how that runs through the ODE. But with PDEs, you have initial conditions and boundary conditions, and that's what makes these kind of interesting to work out. And for problem one, we can see we have a metal pole, half of it's hot, the first half of it's cold, and that's our initial condition. And the boundary conditions are what's known as Dirichlet boundary conditions. And we have both sides of the metal pole set to temperature 0 to say they're dipped in ice. Yeah, and it should say u of 0 t, not x of 0 t. That's just a typo there.
And for problem number 2, we have it as a bar that's of different heat, starting with both sides cold and the middle is hot, and then we have it in an insulated environment and see how that moves out, and that is the Newman boundary conditions. And for this problem, at the temperature, actually that's it. So Andrew will start off with his problem and work it out.
Okay, so the first technique people use to solve these kind of equations is separation of variables. So up top here we have our heat equation. The u of t equals k uxx, and k is our constant that decides how fast the heat disperses. So we can assume that the technique of separation of variables is we assume our solution can be split into two independent solutions that multiply together, that you can have x of x and t of t. So we're saying the temperature is dependent on x and t independently, the position and the time. So what you want to do is get this in the form of the heat equation. So we take the double derivative with the double partial derivative with respect to x and the partial derivative with respect to t, and get these two equations. And what we want to do is substitute them back into the heat equation to get this here below. We have x t prime equals k x prime prime t. And so now we just use basic algebra to separate these variables since they have them equal to each other, like this. And the goal of this is that now that they're separated, we can use ordinary differential equation techniques to find solutions to these separate parts and then later combine them. So to do this, since they're equal to each other, we know they must also be equal to constant. So we bring in this negative lambda. And the reason why we make it negative is you kind of work through these problems and you see what works and what doesn't. I mean, positive lambda does work, but the algebra gets a little more messy, so we're doing it with negative lambda. So when we set these equal to negative lambda, we now have two ODE equations. This first one on the left, which is a homogeneous first order equation, t prime plus k lambda t equals 0. And we know this has the solution from ordinary differential equation c e to the negative lambda kt. And then on the right side here, we have our second order ordinary differential equation, x prime prime plus lambda x of x equals 0. And we can look this up on a table or work it out. that the solution would be in this form. X of x equals a sine square root of lambda x plus b cosine square root of lambda x. So we've been able to split this partial differential equation into two independent first and second order ordinary differential equations. So the next thing we want to do is start including information from our problem. And the first thing we're going to do is impose our boundary conditions. And because our boundary conditions were that either end of the pole is set to 0, u of 0 of t is 0, so for all time, the left side is in ice water, and for all time at location L, the length of the pole, that's also in ice water. So once we split it apart, we have right that. And then that means this above equation has to be 0 when x is 0, and this above solution 2 has to be 0 when x is L. So to solve for b, we let x0 equals 0 using this above equation. So we have a sine of 0 plus b cosine of 0 equals 0. And since we know the sine of 0 is always 0, and the cosine of 0 is always 1, the only way this equation can work out is if our b coefficient is 0. So therefore b equals 0. So we've been able to knock out the cosine from this above x equation. So to solve for lambda now, we want lambda in terms of, just instead of an arbitrary constant, we set x of L equals 0. This is our right boundary condition. And so we have a sine of square root of lambda L equals 0. And we know that sinusoids are at 0 at any multiple of pi. So we know the inside of the sine has to be equal to n pi. So we have square root of lambda L equals n pi. This allows us to solve for lambda in terms of L and n. And L in our problem is 1. We're just kind of the length of the pole 1 to simplify things. So we have square root of lambda equal to this, and lambda equal to that down there. So the next thing we want to do is use a superposition principle to find the general solution of our PDE. So right now we've substituted lambda into our equation, and we have a sine n pi over Lx plus the other t part of the equation, the exponential, decaying exponential. So we combine the a and the c constant to get a sub n. And now we have an infinite number of solutions that are all dependent on n. For every n, there's an a sub n that satisfies this heat equation solution. So what we want to do is find all these a sub n's that will give us the general solution, because the sum of all these mini solutions give us the real solution that we want, and the solution that we want to be able to graph and see, and that apply to our real life condition. So to impose superposition, we want to have the sum of all these smaller solutions, particular solutions. So to solve for these a sub n's, we do this via the Fourier series. So we have, the general Fourier series sine expansion. So we have 2 over L, the integral over the length of the pole, f of x times the x portion of our PDE when we separated it, the sine of n pi over L x dx. So we crunch through this equation, and since f of x is 1 over the first half and 0 over the second half, we just integrate over the first half. And because the function's 1, this is easy to integrate. Sine goes to cosine, you plug it in, and we solve for a sub n, and we get this at the bottom. So now that we solve for a sub n, we know what this coefficient is for any n. So we go back to our superposition equation and plug in a sub n, and we get our final solution. And this is kind of a big solution, and to make sure you did this correctly, we graph these solutions, and you should too. So we use MATLAB, and we just have a nested 3 loop. You loop over time, loop over x, and in this n here, instead of doing it up to infinity, I'll make it back one. Each solution, because there's a decaying decaying exponential, each solution is becoming less and less effective on the overall solution. It's becoming less important because it gets smaller and smaller and smaller. So just going up to 100 gives us a good approximate solution of the correct solution. If you want to be more accurate, you loop that more. If you want to be less accurate, you can loop that less. So for time equals 0, we can see that the sinusoids are trying to attempt to model the initial condition, but since there's a discontinuity, you still have the Gibbs effect, and you can't get the initial condition perfectly. But if you step up time a little bit, you can see how the heat starts to spread out. And we're starting to lose heat off the left end, and the heat's kind of merging over the right end. So if you increase time a little bit more, the heat spreads out more, and eventually this thing will decay down to the flat line at 0, which means all the heat is exited through the two ends of our function.